In this video, I'm going to do one of the chapter 13 test problems from the textbook. So this is on page 858. I'm looking at question number 8. So this is another airplane problem that's moving around in certain directions with certain speeds, and you're trying to figure out what the final true speed and direction of the plane is. So this is a problem that involves a triangle, and all of these triangle problems can be solved using the law of cosines and law of sines, or with vectors. So I find it easier to do the vector method on these problems, but I'll show you how to do it in both ways so you can pick the one that makes most sense to you. So we have a point A, that's where a plane starts off, and it's going to move 370 miles from point A to point B with a bearing of 24 degrees. 24 degrees. So for bearings, we always measure it from the north axis and then go clockwise. So the 24 degrees is down there, and the plane's moving this way to point B, and that's a 24 degree angle. And then it moves 240. Let's put the 370 miles in here. It moves 240 miles from point B to point C at a bearing of 37 degrees. So again, we can measure the bearing from up here, 37, and it's going to go that way to point C, and this is 240 miles. And then we figure out that we want to know the direction from the beginning to the end, the distance and the bearing. So we're trying to figure out what that angle is, so we can add it to this to get the bearing, and we want to know what the length of this side is. So with vectors, I can write vector components for each of these sections. So the first bit is my A to B vector, and that would be, I need to figure out two components. I can make a right triangle here, where I have this 24 degree bit and the hypotenuse is 370. I'm not going to use 24 degrees as my angle. I'm always going to use the standard position angle. So I'm starting on the horizontal and going this way. So that would be 90 minus 24 is 66. So I'm actually going to use 66 degrees for that angle. So it would be 370. And then the x component is cosine of 66. And 370 sine of 66. In this particular problem, it doesn't matter because we're moving up and right in all of these directions, so both x and y are positive. You always want to pick the standard position angle though, especially if you're going this way or if you're going in one of the other directions where x and y could be negative, because then if you pick the right angle, the sine just gets taken care of for you, so you don't have to manually add in a sine over here. If you did choose 24 degrees, you would still be able to do the problem. You just have to remember to put in an appropriate sign in the right spot. So really, like this, the triangle I've solved for here is this triangle instead. Same kind of deal. If I use this triangle, it would be the sine of 24 as my horizontal component, but I've used a cosine of 66 instead. Then I figure out my BC vector. So again, I want the standard position angle. So that would be, this is 37 degrees. I want this bit, which is 90 minus 37, which is 53. And my hypotenuse is 240. So I do 240 cosine 53. That's the other advantage to always using your standard position angle is, and I just make a mistake as I say that. The x component is always a cosine of an angle. The y component is always the sine of an angle. And so now if I want to figure out AC, the vector for that is just adding these two up. So my vector is 370 cosine 66 plus 240 cosine 53 degrees, comma 370 sine 66 degrees plus 240 sine 53 degrees. So now to get the length of AC, I can think of that in terms of magnitude. The magnitude is the square root of 370 cosine 66 degrees plus 240 cosine 53 degrees squared plus 370 sine 66 plus 240 sine 53 degrees squared. And I'd have to put all of that into a calculator, which I don't seem to have it here right now, but I can go get it real quick. So I do 370 cosine 69 degrees. Yes, I am. Okay. So 370 cosine 66 plus 240 cosine 53, and then square that, and I add on 370 sine 66 plus 240 sine 53, square that. Oh, I took that in wrong. 370 sine 66 plus 240 sine 53 squared. So that, add this to my cosine bits, and then square root it, and you get 606.257 miles is my total distance. So that means this side is 606.257. The other thing I can do is get the bearing for it. So if I figure out what this angle is, I can subtract the 24 and this away from 90 to get the middle angle, which is what I need to get, because I need to get the bearing, so I need to get that angle. Yeah, so this is my AC vector. My x and y components are giving me this bit and this bit. When I take the inverse tangent, I'm going to get this angle, but the actual angle I need is this angle. This is my bearing angle. So I take the inverse tangent of my y over x. So let's do that. So that's going to be... You want to make sure you are using the exact values, so it might take some time because you need to make sure you're storing all of these numbers in. But make sure you're using exact values when you calculate this, because if you keep rounding along the way, those rounding things that you're doing are going to add up eventually and make your final answer really off. So usually when we grade your solutions, if it's within, like if only the third decimal place is off, then usually we're okay with it. But if it's more than that, then you kind of want to check that. So I'm getting 60.891 degrees, which means this bit is the 60.891 degrees. My bearing is 90 minus that. Which will give me the 29 point something. 29.109 degrees. So this is my bearing, and this is my distance. So I'll make another video showing you how to do this with the law of cosine, so you can see it the other way.